Hello, this is Byron Washburn. Today I like to talk about damped driven oscillations. Okay, so what I'm going to have is I'm going to have a damped oscillator system like what we did before, except the difference is I'm going to have some driving force acting on the system. So f of d of t is some force as a function of time that drives the system. That force could be any arbitrary function. It could be a constant. It could be a linear function. But for now, I'm going to introduce a sinusoidal driving force, okay, where F naught is the magnitude in newtons of the force, and then omega is the frequency of the drive frequency, okay. So I want to look for solutions of the position as a function of time given a drive frequency omega. Now, thinking about time scales, that drive frequency is going to set the time scale for the problem. So I can define a time, TD, as with respect to that drive frequency. Okay. Now, physically, this might be a system. It's hard to envision how do I apply a sinusoidal or a drive force on the system. So it's a little hard to envision how you actually do this in practice, but it's a good problem still to look at in general. So what do I have? Again, what I have is I have a damped driven oscillator. I have the same differential equation before, except in the previous case it equals 0, now I have a driving term here. So in terms of differential equations, I have a second order ordinary differential equation. It is now inhomogeneous because of this non-zero term on the right. Okay, so we know how to solve this from what we talked before. We use the method of undetermined coefficients. And then what we can do is we can say the solution is going to be equal to, well, it's going to be a sum of the homogeneous solution, okay, and then what's called a particular solution. All right. Now, what's the homogeneous solution? The homogeneous solution, I set this equal to 0. That's the solution for this differential equation equal to 0. Well, we know what that's going to be. Okay, that's going to be either an underdamped, overdamped, or critically damped system, depending on the values of beta, and omega. And so for the sake, so I have to choose a particular case. And for this problem, I'm just going to look at a underdamped system. So where beta is going to be less than omega naught. Okay, so this is, and it doesn't matter what we pick. But that's what I'm going to do here. It just makes things a little nicer to plot. Okay, so I'm looking at an underdamped solution. Now, there's one important thing to think about. Remember, for all the homogeneous where there's underdamped, overdamped, or critically damped, that solution goes to 0 as time goes to infinity. Okay, that's true for all those three cases. So what I can say is that, as t goes to infinity, x goes to 0. And why is that? Well, because the dampening force continuously takes energy from the system and eventually it stops and x equals 0. So what does that mean in this case? Well, this means that in our problem, our solution is the sum of the two. After some particular time, this is going to go to 0. So then this guy here is still going to be not 0. Okay. And so this thing here, we call it a homogeneous solution, but there's a better name. We're going to call this a transient solution. Transient means that it's there for a little bit of time, then it goes away. So then the only thing that's going to be left is this solution here. And this is really what we're interested in solving this problem. And in fact, we can give that a name. That is called a steady state solution. Okay. And what does steady state mean? A steady state solution. Okay. Steady state means that, well, I wait a little bit of time for all the wiggles to go away, and I look at a motion that repeats over time. So that's why I'm really going to be interested. So at long times, what do I expect? At long times, I expect is that the motion is going to be just that particular solution. And since whatever that, remember in our particular solution, we guessed a form. Well, I would guess a form of a sum of a sine and cosine, but all those sines and that sine and cosine will oscillate with omega. So what I expect is that at long times, x will eventually go to the particular solution. The particular solution will have a frequency of omega. Now it might be cosine omega, might be sine omega, or it might be something in between, but with some arbitrary phase. And that's what we're going to expect to see. Okay. So what I did here was, okay, again, what I expect is at long times the solution is going to go from it's going to be the solution, the transient solution is going to die out, and then I'm going to have this particular solution. So here what I did below was I just wrote what I would expect. If I had to solve this differential equation, one way is guessing a form for the particular solution. I would say it's going to be some sum, a constant c, cosine plus d sine. Now another way of writing that is basically saying I have my particular solution is going to look like a cosine of omega t minus some phase. Now notice that depending on the phase, this is a cosine or a sine, but it does oscillate with omega. So in the end, the problem to solve, so I expected this solution, okay, after the steady state solution, I expect it to look like this. So the problem comes into just solving for a and delta. That's it. Okay, so that's what we're going to do. In the end, what we're going to do is we're going to get a and delta. That's how we're going to solve this differential equation. Okay, so however, before that, we're going to solve this using complex numbers. So I want to review the concept of complex numbers, and hopefully this is a review. So what I want to do is let's talk about complex number. So z is going to be a complex number. I can always represent a complex number as a plus ib. I think you know that. And so a is the real part of the complex number, and b is the imaginary part, kind of looking here. However, a more different way of doing it, and a more useful way, in my opinion, is writing a complex number as an amplitude times a phase. And we can relate a, b, and a and delta by a right triangle. So here I have the real part of z on the x-axis, the imaginary part of z on the y-axis. A is the x component, b is the y component. But then how do I get a? A is the hypotenuse of that triangle. So a, which is called the amplitude of the complex number, is a squared b squared square root. And then delta is the phase, which is the tangent of this over this. Now there's a minus sign here. This is what your book does. Some books would use, I'd rather use a positive sign here, but I'm following with the way your book does. But it really doesn't matter. And so I just put a minus sign in front to get the correct phase. Okay. And the phase tells me, complex number tells a real part, imaginary part. If the phase is 0, that means my complex number is a real number. If the phase is 90 degrees, that tells me my complex number is completely imaginary. So that's one way of thinking of it. A couple other operations we can do. There's something called the complex conjugate, and that's z star. All I do is I just put a minus sign there. Wherever I have, I turn I to minus I, and that's what I get here. The magnitude, again, is just using this right triangle. The magnitude is always the one way of writing it. It's always equal to z times z star square root, and that will also give you this expression here. So that gives me a, and then real and imaginary parts. Okay, so how we're going to solve this differential equation? Well, the way we're going to do it, this is my differential equation I'm going to solve. And again, really what I want to get is I know, okay, let's just go ahead. I'm just going to talk about the solution and then show you the answers. We'll actually do all the math in class. So I have this differential equation here, and notice I have a cosine here. What I'm going to do to make life easy is I'm going to solve this as, I'm going to turn x into z, where z is a complex number. And then I'm going to guess an exponential solution and then use that to solve. So I can and in the end, what I'm going to do is take this differential equation here, right, in terms of z, and then I'm going to take the real part of it in order to get the solution. Now if I do that, this becomes z, this becomes z, this becomes z, and then cosine, this becomes e to the I omega t because of the Euler relationship. Okay. And then what I can do is I can guess exponential solutions, stick it in. All right. So then from that, I'm going to get, remember, so I'm going to get this constant c. Again, c is a constant. Okay. And remember, now c, remember, z is a complex number. This is complex. C is also a complex number. Okay. And so what I get is by substituting and subtracting, I get an expression for c, but c is a complex number. And in the end, what I'm going to do is I'm going to say c is equal to, using complex notation, is a, where a is a real number and delta is a real number, equal to a times e to the minus delta, I delta. And then a is what I'm going to call the amplitude, and delta is the phase. Okay, so I'm going to get expressions for a and delta. We're going to do this in class. But let me show you the solutions, and we're going to talk about the solutions. Okay. So by doing a little bit more math and basically algebra, what I can get is I can get these solutions. Okay. So what I can do is I can say, okay, again, my complete solution is the homogeneous part plus the particular part. The homogeneous part is the solutions we get for underdamped, critical damped, and overdamped. And this is called the transient solution because this will go to 0 as t goes to infinity. And then what happens is, okay, now then what's going to be left over is a particular solution. It looks like the form A cosine omega t. So it oscillates with the drive frequency, but has a phase delta and A. An important thing is that amplitude and delta depend on omega, which is the drive frequency. Okay, so this is my complete solution. All right. Now what's really important to do at this point is to talk about what does A and delta mean, and how does A and delta depend on frequency. All right, that's what I want to do next. Okay. So again, long-term behavior as t goes to infinity, the solution goes to the particular solution, which I wrote before. What is A? Well, A is the steady state amplitude, oscillation amplitude. As you wait a little bit, you're going to have a steady state solution. A at a given drive frequency, omega, is going to be the amplitude of the oscillations. That's pretty straightforward. What is the phase? What is delta? Well, delta represents the phase difference between the drive frequency f cosine omega naught and the oscillation frequency. If you notice, look at both of these guys. They're both cosines. But there's a phase. If I subtract this argument from that argument, I get delta or minus delta, depending how you do it. That's going to be the phase difference between the drive frequency and the oscillation frequency. Okay? And that's going to, and notice that, going back to my solution, A depends on drive frequency and delta depends on drive frequency. Okay? So let's take a look at some possible solutions. So here, what I'm going to do is I have a program called Physics 522 damp driven oscillator. Okay, and in this program, what I do is I solve the differential equation. I actually solve it using Runge-Kutta. But what I'm going to do first is I'm going to plot A and the phase delta. Now, just give some parameters in this program. What I'm going to do in this program is I fix the natural frequency to 5 times 2 pi. Why do I do that? Well, I'm basically going, your book has an example 5.3, and I'm using those numbers from your book. Okay, so I fix the natural frequency. Thus, I have a natural period. Your book also, you remember you have a choice. You know, I could choose underdamped, overdamped, critical damped. Your book uses underdamped situation. Okay. So then what I'm going to do is now this is my drive parameters. I'm going to use 1,000 newtons. And then I'm going to first just drive it at so first thing I'm going to do is I'm going to drive it at a frequency that's lower than, okay, well, let's plot let me first plot the amplitude and the phase as a function of frequency. Okay, so you notice that, so this is the drive frequency in radians per second. You notice it kind of stays here, kind of peaks here, and goes down to 0. This frequency here corresponds to the actual natural frequency of the oscillator. So you get this peaking effect at the natural frequency. And that's easy to see if you just look at this equation here. Back to my solution, I'm going to get the smallest denominator. When omega is equal to omega naught, I'm going to subtract this. I'm going to the smallest thing and divide by the smallest thing, and this is going to be the largest thing. Okay, so that's what's happening there. Now, if you look at the phase, you notice the phase goes from 0 phase. So this is the axis here in multiples of pi. So this is 0. It comes up to here. I get half pi, or pi over 2. And this occurs also at the drive omega naught, not the drive. Remember, omega naught is the natural frequency. So the natural frequency for this particular problem is 5 times 2 pi. So if let me type in what is, sorry about that. So if I type in omega naught, notice that's 5 times 2 pi. So it's 5 times 2 pi, and that's 30. Remember, this is 31. That's what that number is. So this corresponds to the natural frequency omega naught. okay? And I'm plotting it as a function of drive frequency. So notice that it peaks, the amplitude peaks at that, and then the phase at that is going to be pi over 2. All right. Now what I'm going to do, let's take a look at the oscillations, okay, as a function of time for different drive frequencies, okay? Okay, so what I'm going to do here is I'm going to do the numbers that are in book example 5.3. And in your book example, what they do is, again, the natural frequency is 5 times 2 pi. The drive frequency is going to be 2 pi. That's what they do, okay? And what I'm going to plot is, so let me explain what I'm plotting here. I'm plotting, this is the drive frequency. Notice it's a cosine, okay? And then this is x as a function of time. All right, and this is actually a figure in your book, but let me explain what's going on. Notice that you have all these wiggles kind of going like this, and then eventually as a function of time, you get to this solution right there, okay? So what's happening at times less than 2 seconds, I have really, my solution is a combination of the homogeneous plus the particular solution. And so this is these wiggles are due to the transient solution, or the solution for the underdamped solution. So the underdamped solution kind of dampens out, it goes away, and then what's left over is the particular solution at longer times. Okay. So when I want to look at the steady state behavior and say, okay, what time do I need to look at beyond the steady state behavior? Well, obviously for times less than 2 seconds, I do not have steady state behavior. I have the transient behavior. And then if I look at times longer than 2 seconds, I have the steady state behavior. Okay. And that's going to be true when we look at all these systems. There's always going to be this short time behavior, which I really don't care about. Transient behavior, really I'm interested in the steady state solution. Okay, so that's what's happening there. Now what I want to do is I want to look at the steady state solution as a function of drive frequency. Okay, that's what I'm going to do next. Okay, so now what I'm going to do is I'm going to choose the, again, remember I'm keeping the natural frequency constant, but I'm changing the drive frequency. The drive frequency is going to be half of the natural frequency. Okay, now let's take a look at the solution. All right, so actually before I take a look at the solution, let's look at the amplitude and phase. Okay, so remember what I did was the drive frequency is about 31. The natural frequency is 31. What I'm doing is I'm driving at half of that, so that's at 15. That's here. As you can see, the amplitude should be about 1.7, 1.6 or something like that. Okay. Now let's take a look at the solution. So you can see, all right, well, it's a little bit less than 1.5. But you can see the long-term solution, the amplitude is about 1.5. So that's consistent with my graph here. It's hard to read at 15, but yeah, okay, 1.5, I can believe that. That's 1.5 there. That should be the amplitude of the oscillations. I look at the amplitude here, I got about almost 1.5 in the steady state. All right, now let's look at the phase. The phase at 15 is here. It's pretty dang close to 0. That means that there's going to be nearly a 0 phase shift or difference between the drive frequency and the solution. And you can see that if I take a look at this peak here, that peak lines up with that drive frequency there. I take a look at this peak here, it lines up. So there's 0 phase shift between the drive frequency and the oscillation. Okay. So now what I'm going to do, I'm going to look at the case where the drive frequency is equal to the natural frequency. Okay. And actually let's predict. What I should predict is that, okay, that's when the drive frequency is equal to this point here. I expect the maximum amplitude about 10. And then the phase should be pi over 2. Okay. And remember, if a cosine of an angle plus pi over 2 is sine. Okay. Or maybe it's minus 10, but anyhow, it's a sine. So let's just do that. Okay, run it. Okay, so take a look here. Again, looking at the steady state solution. Let's look at the amplitude. The amplitude here is, oh look, that's 10. Okay, so that's 10 there, and that's 10 there. That's great. Now let's take a look. If it's sine, that means that the 0 of this guy is going to line up with the peak of there. And just kind of looking at it, you can see, oh yeah, that 0, that time is right there. So this looks like a sine, and then this looks like a cosine. Okay, that's great. So you can see there, again, the phase is the phase difference between the drive frequency and the actual oscillations. And there's a pi over 2 phase shift there. Now let's look at the high frequency behavior. So again, I'm going to pick, in that case, I'm going to pick this to be 2 times. So that's going to be 2 times 31. That's 60 something. That's going to be out here. Okay. The amplitude is going to be quite small. It's going to be smaller than what we had before. We had 1.5. It's probably going to be 1 or less than 1. And then the phase at 60 is almost pi. So where I expect a peak in the drive frequency, I should have a trough in the oscillation. Let's see if that works. Okay, take a look. Now we have to really look at the steady state behavior. I may need to go a little bit longer time, but actually we can kind of see here the amplitude. You can see the max amplitude. There's a little, so you can see here there's a little more transient effects than we want, but still the amplitude is about 0.4. What did we say it would be? We said it'd be less than 1, and okay, that makes sense. It's less than 1. Okay, and then notice that the peak of this lines off with the trough of that. Okay. Now it looks like we have to go for even a longer time scale. So what I'm going to do here is I'm going to pick, so I'm going 20 times that. Let's even do 30 times that, a longer time scale. Okay, we can do that. And then we have to look way out here. So you can see here, there's still some transients going on there. And then here, the transients, so the transients have died down quite a bit. I guess that makes sense because remember, since I changed the frequency oscillation, we said transients die down after 2 seconds. So I have to make sure that when I look at this data, I have to look on times bigger than 2 seconds. So I have to look out here. So I need more. I need 30 times the drive period. So you can see here that I have a peak here and I have a trough here. Okay. And what I did here, like I said, you should never believe me. So what I did was I took the same graph. Again, I'm driving at I have a drive frequency that's 2 times the natural frequency. And here I zoom in from a time of 2.5 seconds to 3. I'm beyond 2 where the transients definitely have died out. And take a look. Here I have a peak and I have a trough here. And that means that this guy's cosine, this guy is minus cosine, so the phase shift is pi, or very close to pi. And remember, my drive frequency is about 60, and that's what I get from here. Okay, so one thing you should definitely be able to do is try, if I give you a damped-driven oscillator, you should be able to describe the motion in these 3 cases. The 3 cases are, at a drive frequency less than the natural frequency, on resonance, which is drive frequency equal to resonant frequency, and then when a drive frequency is bigger. And you should be able to describe that both using equations and in words. All right, that's something you should be able to do. Now, the last thing I want to do really quickly is talk about this concept of resonance. Notice how I have a peaking going on here. Remember what is a drive frequency doing? It's adding energy to the system. And so the resonance is basically defined as the efficient transfer energy from the drive to the oscillator. And that most efficiently happens when I drive the system at the natural frequency. Okay. And you've done this throughout your entire lives. As you're pushing somebody in a swing, there's a frequency that to push somebody that you have most efficient transfer of your energy to the swing motion. Okay. Now we're going to look at this in the context of a homework assignment, but notice what I have here is I have this kind of function here, and this function is given by what I showed you earlier. We're going to define a couple things. Actually, let's take a look at the functional form just real quick. Notice that, okay, what I'm going to plot, actually notice what I plot here. I actually don't plot A, I plot A squared. All right, why do I do that? Well, really, the X depends on A, but the energy system, which is potential energy plus kinetic energy, is going to depend on A squared. That's the power delivered or sucked up by the system is proportional to A squared. So if I look at A squared, again, what is A squared? A squared I didn't write a squared there, but I write it here. A squared is basically this thing here. And notice that then I at omega equal omega naught, I'm going to get the smallest denominator, and this thing is going to peak. Okay, that's called the resonance phenomenon. So I get the most peaking occurring, and the width of this guy is going to depend on beta. That's actually really interesting. So we can define something called the full width half max. If I take this value and divide this by the peak value, look at half the value. The width of that is going to be 2 beta. That's really interesting. So the width of that peak depends on the dampening. Okay, all right. And so then we can also define a quantity called a Q factor. Okay, which is a measure of the sharpness of the peak, as well. It's the center frequency divided by the width. Now you can show that the Q is actually equal to some very physical things. First of all, Q is, you can show this. You'll do some homework. Q is equal to decay time divided by the period. Again, what is the decay time? That is how much energy is lost. And the period, and that's the natural period, that is how much, that tells me the rate that energy is sloshed between kinetic and potential energy. Okay. So, and then also you can show that the Q is really equal to, and this makes sense too, is the total energy divided by the energy dissipated. Okay, so if you have a lot of energy that's lost, your peak is not going to be very peaked at all. It's going to be kind of a squash thing like that. The smaller beta is going to be, the more peaky this thing is going to be. And so Q is a measure of how efficient your drive frequency overall, given the dissipative forces, transfers energy to your system. And finally, let me talk about phase again, because phase is something people just get confused about. And again, what does the phase mean? The phase is the phase difference between the drive frequency and the oscillation. And we have 3 different cases. So if I have a drive frequency that's less than that natural frequency, and that occurs somewhere here, that the phase shift between the drive frequency and the oscillations is 0. So they're in phase. Okay, I said no phase shift. I would say that's in phase. Okay. Now, if you're on resonance, then this phase occurs, the phase shift is power 2. And then, so what that means is the drive frequency looks like cosine. The actual oscillations look like sine. Okay. In engineering terminology, we say that these two are in quadrature with each other. Okay. So that's what a pi over 2 phase shift. And then if you go for long frequencies or high frequencies where omega is greater than omega naught, the phase goes to pi. And again, why does it do this? Because this functional form is that of an arctangent. Okay. And so then the drive frequency is omega, say cosine omega naught, the amplitude is minus, and that's where that minus phase. So again, that's what the phase represents. Okay, so that's it. We're going to do a lot more with that. We're going to look at power and stuff like that. Anyhow, this is, again, we're summarizing this as a summary. Again, what we've done is we've looked at a damped-driven oscillator. We've solved this differential equation. There's going to be a transient solution given by this, a steady-state solution. Really, we're interested in the steady-state solution, which is going to look like, A cosine omega t minus delta. We got functions of A and delta as a function of drive frequency, and we talked about how the system oscillates under that particular drive frequency. Okay, that's it. We'll see you later. Bye-bye.